Hello and welcome back to PC Retro Programmer. In this series of videos we're drawing circles, and I thought it would be great to sit down and actually work out how to actually do this from first principles. So the algorithm that we normally use is called the Midpoint Circle algorithm, and you can see it over on the left here. In appearance it's very similar to the Bresenham line drawing algorithm, and it's actually not that much more complicated to implement. The only real downside with it is it only draws an eighth of a circle for you, so you actually need to use the algorithm 8 different times with slight modifications to get the 8 octants of your circle. So instead of just deriving the midpoint circle algorithm though, I thought it would be fun to extend it a little bit. It turns out that without too much more effort you can actually draw ellipses using a very similar algorithm. And whilst I can find hundreds, literally hundreds of write-ups of the midpoint circle algorithm online, I've so far been unable to find a description of the midpoint ellipse algorithm. And certainly can't find a derivation if it's out there somewhere. So in this video what I'm going to do is start off by deriving the midpoint ellipse algorithm. And as I say, it's not much harder than the midpoint circle algorithm, and I'm going to try and make really light work of the mathematics so that it's really straightforward. Now let's suppose that you want to plot an ellipse. You probably already know by now that an ellipse is just a squashed or a stretched circle. And so instead of having a consistent radius r all the way around, it actually has two radii called semi-radii. So one would be length r, say, and the other one will be length s. Now, it turns out that we're only going to consider the case where the semi-radii are in alignment with the axis. So if you want to plot an ellipse which is rotated somehow, you're going to need an additional transformation afterwards, once you've figured out the points for the upright ellipse. But that's a topic for another video. So the way it works is that we start out with the equation of an ellipse, which you can just look up on Wikipedia. And if you plug in r equals s here, you'll just get the equation of a circle, since a circle is just a special case of an ellipse. And what we do is we expand this out, so basically just clear the denominators, move everything to the left-hand side, a couple of steps of basic algebra, and what we'll end up with is that this expression has to be 0. And so what this means is that for any point exactly on the ellipse, x, y, when I plug those coordinates in, I'll get exactly 0 for this expression. So the very first point that we plot, r, 0, must be exactly on the ellipse because the semi-radius here is exactly r, and so if I plug in r, 0, this should be exactly 0, and you can actually check that that's the case. But for other points on the ellipse, we don't necessarily have the luxury of picking pixels that are precisely on the ellipse. They might be a little bit off, and our job is to find the pixel which is closest to being on the true ellipse. So, for example, if we've just plotted the point xi, yi here, because the ellipse initially starts going up and to the left, there's only 2 pixels that we could choose for the next one, either the one directly above it or above and to the left. Those are the only possibilities, and so our job is to plug in the coordinates of those pixels and try and find the value which most closely matches this, in other words, which is closest to 0. So if I go directly up, the only thing that happens is yi increments, and so I end up with xi, yi plus 1, and if I plug those in, this is the expression that I get. So you can see xi and yi plus 1 plugged in here. If I go up and to the left, then I plug in xi minus 1 and again yi plus 1. That's the same in both cases. And you can see that I've plugged those in here, so this is the expression that you get. So our job is to figure out which of these is closest to 0. Now there could be positive or negative values, so we just take the absolute value, and then the question becomes which of these absolute values is smallest. That'll be the one with the value closest to 0. So let's suppose that this absolute value is actually bigger than this absolute value. That would mean that this absolute value is the smaller one, and this one came from this point, the point on the left. So in other words, our condition becomes this. We're always going to increment y. You can see that y went up by 1 in both cases, but we only decrement x if this inequality holds, because in that case that would be the smaller absolute value, and that would mean we'd have to pick that pixel. So we go left, we decrement x if this holds. Now these absolute values are a little bit annoying to deal with in algebra, but one way of getting rid of them is to square the values. You remember that if I square a value, I get the same answer as if I square the negative of the value. The sign actually doesn't matter. And you remember also that all the absolute value does is at worst change the sign of the value. And we just said that if we square, the sign doesn't matter. So in other words, if we square these values, we can just ignore the absolute values and throw them away. So we'll actually replace them with squaring instead. Now from here you have to do a little bit of algebra, and I'm just going to omit the steps, but basically if I expand out this side, there's a square here now, and I'll get one very long expression, and if I square this side I'll get one big long expression. And then I'm going to move all the terms on this side onto this side of the equation, so I get one huge expression greater than 0. Now you can proceed by hand, but you really have to know what you're looking for. So it's actually easier just to use a computer algebra system at this point. So you could use Maple, or if you want a free open source one, use Sage, or there's a new one called Oscar. And so basically I take this big long expression that has to be bigger than 0, and then I factorize it. So the computer algebra system will tell you that there are 3 factors: 2xi minus 1, s squared, and this big long thing in brackets here. Now it turns out that this condition, that this big long expression has to be bigger than 0, can be simplified. First of all, this value 2xi minus 1 is always positive on this first octant of the ellipse. So I can actually ignore that, because multiplying by a positive value doesn't change the sign, and so basically it's going to be greater than 0 whether or not I multiply by that positive value. So that gets crossed out. And s also should be positive. I mean, if it was 0, we'd just be dealing with a horizontal line, not an ellipse. And we already know how to deal with horizontal lines. So s should be positive for a real ellipse. And so I can just cross that out as well, since it's also not relevant. So we just ignore these, and this is really our condition. This long thing has to be greater than 0. Now initially that looks pretty messy, but if you take a look at this portion here, this is exactly this expression with xi comma yi plugged in, so the coordinates of the current point. So what we're actually going to do in this algorithm is we're going to keep this value, which I've called d, up to date every iteration for the coordinates of the current point, whatever it is that we've just plotted. And then I'm also going to keep 2 other values, dy and dx, up to date. And then the condition will just become 2 times d plus dy plus dx has to be greater than 0. If it is, then we take the pixel to the upper left. If not, we take the pixel immediately above. So this is a much simpler condition. You just have 2d, dy and dx to consider. So now, once we move to the next pixel, we'd need to update all of these values for the coordinates of the new pixel. And this turns out to be pretty easy to do, since there are only 2 possibilities. Either we just incremented yi, and you can see exactly what happens to d if I increment yi. If I plug in yi plus 1 in here and expand out the square, this value will go up by r squared times 2yi plus 1. This expression will go up by 2r squared, and this one won't change. And if I decrement x, then this one will go down by s squared times 2xi minus 1. This one won't change, and this one will go up by 2s squared. So it's actually not difficult to compute the new values for each of these. It's just a small modification that we have to make in each case to update them from the next pixel, whichever one we happen to choose. So that's how this algorithm is going to work. There are going to be 3 values that we keep track of, and of course we need to figure out what their starting values are, but that's easy since we know the starting coordinates r comma naught. And if I plug in r comma naught here, and naught here, and r there, then I actually get the starting values of each of these, and then I just keep them up to date every iteration by figuring out how they change if I move up or if I move up and to the left. Now in this video and the few on plotting circles on the channel, I'm going to only be using the version of this for a circle which has r and s equal. Now if s is equal to r, then we actually have a factor of r squared that we can take out all the way through this inequality. And so once I cancel that out, I end up with a much simpler expression, and that's the one that I'm actually going to use in this video and the ones on drawing circles. In a later video, we're going to come back to the more general expression and learn how to plot an actual ellipse instead of a circle. But that's a topic for a little later video. Now in our derivation, there were 2 minor points that I glossed over. The first was that we took the mathematical convention of the y-axis pointing up, but on the screen the y-axis actually points down, but it's really not a big deal. I mean, basically the ellipse is going to be drawn down and to the left instead of up and to the left. Well, whoopee, I mean, we've got to draw all 8 octants of the ellipse anyway. All that's going to happen is they're just going to be drawn in a different order, so it really doesn't make any difference. The other thing that I glossed over is that in the derivation the center of the ellipse was 0, 0. But when we go to draw an ellipse on the screen, we really want to be able to put it anywhere. So the center would be at coordinates x0, y0, and those would be passed into our ellipse function. Well, it turns out that the way we're actually going to draw this ellipse is we're just going to start at a particular starting point, and this is where we really do need to use the x0 and y0. We need to add those to the values that we had in a derivation, which were just r and naught. And then from that point on, all we're going to do is either move up or move up and to the left. So we're just always going to be doing relative movements from that point. Now in the actual algorithm down here, it looks like we're actually using coordinates, but when we come to the actual implementation, you'll see that that's not actually what happens. We actually just do everything with relative movements from a starting point. And so this is actually the only point that we really need to use the x0 and y0 center coordinates that are passed into the algorithm. Now in order to make an algorithm out of this, what I've done is pulled the equations off the sheet of paper where we did the derivation, and this is the big long inequality that we have to check to determine whether to take the upper left pixel or not. And you can see that I've pulled the 3 terms that I talked about, d, dy and dx, out and written them out in full above here. Now we could actually go ahead and actually make an algorithm directly from all of this, but it turns out there are some simplifications that we can make. And so what I'm going to do is make a series of transformations, and they're actually going to leave us with slightly different values for these 3 terms, but in the end the implementation itself will be simpler. So the first thing I'm going to do is to replace this dx here with the 1 minus 2xi, which is on the previous line. And this is going to mean that we don't need this line anymore because dx doesn't appear anywhere else. And then I can actually get rid of the plus 1 here, and the reason is that I can just make this a greater than or equal to 0, and then the plus 1 is not needed. And now I see that the entire equation is divisible through by 2. So let's get rid of the 2's since we can safely do that, and now everything is just a little bit simpler. So the next thing I want to do is work out some starting values, and d itself actually starts out with the value 0, and that's because the first pixel that we plot has coordinates r, 0, and if I plug in xi equals r and yi equals 0 into this expression, I'll end up with d equals 0. So that'll be the starting value, and that makes total sense because the first point that we plot is exactly on the ellipse, and so the d value should be exactly 0. And of course that first point has coordinates x equals r and y equals 0, so those are the starting values for xi and yi. So we now have the starting values that we need. Now the next thing that I want to do is figure out what happens in the case where xi has to go down by 1. That happens when you pick the upper left pixel. So obviously this xi will decrease by 1, but the value of d will also change. You can see that if I substituted xi minus 1 in here and expand out that square, then I would end up with a value of d that was 2xi minus 1 smaller. So d would go down by 2xi minus 1. And so somewhere in the algorithm we'd need to decrease d by 2xi minus 1. But instead of doing that, I'm going to make a little change here. I'm actually going to decrease d by 2xi minus 2, and obviously that's not the right amount to decrease it by, and this is in the case where xi is decremented, so in other words when we pick the upper left pixel. But if this value d is going to go down by 1 less than it should in our algorithm, then we need to compensate that somewhere. And the way we do that is to make xi itself go down by 1 less than it should in this expression. So in this expression, this is the case we're dealing with where xi is decremented. Xi is just going down by 1 in that case. So if we make it go down 1 less than it should in this expression, it won't go down at all. In other words, it will keep the same value throughout the whole algorithm. So this term here will actually just be r, since that's the starting value of xi, and it's now not changing. So that's why we make this little change. Instead of decreasing d by 2xi minus 1, we decrease it by 2xi minus 2, and we compensate that here, and that means that we end up with a constant here instead of xi. Now it's only going to affect this expression here, so we don't need to make any changes elsewhere for that. So now we can actually get rid of this minus r as well. We can just consider that as being part of d. It's just a constant, so we can just merge it in with the d, and we'll just start off with the value minus r. And now d is less than the original value by r, and that takes care of the extra term that we had. So now we have a much simpler expression for our inequality. So the next thing I'm going to do is plug in dy, and that will be 2yi plus 1 according to the previous line. And so now we can actually get rid of this dy since it doesn't appear anywhere else. And I want to think about what happens in the case where yi gets incremented, and that will happen all the time. Basically it doesn't matter which pixel we choose, we have to increase yi by 1. So obviously yi will go up by 1 here, but d will also change. This yi will go up by 1, and if I plug in yi plus 1 here and expand out this square, then d will go up by 2yi plus 1. So this is a little bit closer to what the final form of the algorithm will be. So I actually don't really need this expression d anymore on the top line, so let's get rid of that. And these are the equations that we're left with. Now, just to make things a little bit tidier, I'm going to write dx equals 2xi, and I'm going to write dy equals 2yi. Now, these are not the original values of dx and dy, that's just what I'm going to use in my algorithm. So let's go through and use those instead. So this will be now dy, this will be dx, and this one will be dy. So this is the final form of everything. We've got the starting values for everything, and we've got the change that we need to make to d if xi is decremented, and we've got the change we need to make to d every iteration when y is incremented, and these are the new dx and dy. So now let's check the algorithm below here and make sure everything's correct. And the first thing we'll look at is all of the starting values. So dx is 2xi, and xi starts out as r, so dx must start out as 2r, so that's correct. dy is 2yi, and yi starts out as 0, so dy must be 0 at the start, so that's correct. And of course d starts with the value minus r. We already computed that above here, so that's correct. And we know that these are the starting pixel coordinates, so we don't have to look at those. So the next thing that we have to do is we have to decide whether we're going up and to the left or just straight up, and for that we need to evaluate this inequality here. So the first thing we need to do is to add dy plus 1 to d, and then we need to check if the result is bigger than or equal to 0. So that's these two lines here. We add dy plus 1 to d, and we check whether the result is bigger than or equal to 0. Now it's actually really convenient that we added dy plus 1 to d here, because this is something that we need to do every iteration of the loop anyway. So that actually takes care of that line as well. So that's already dealt with. Now if the condition does hold, then obviously x is going to be decremented, and then what we need to do in that case, this is it here, we need to decrease d by dx minus 2. So the way we can do that is, first of all, subtract the 2 from dx, and then subtract the result from d. So that's these two lines here. We subtract 2 from dx, and then subtract the dx from d. And again, it's really convenient that we're actually subtracting 2 from dx here, because if xi is going down by 1, dx is going down by 2, and so that's exactly what we need here anyway. So it's really great that we've already done this just in evaluating this step. So the final thing to check is the value of dy. What happens to that? Well, that's going to increase because y is incrementing every iteration of the loop, and so if yi goes up by 1, then dy goes up by 2, and so that takes care of the final line. So everything here matches exactly what we've derived, and so this is the midpoint circle algorithm. And what this means is that we can go ahead and implement this. Now there's lots of write-ups of the midpoint circle algorithm, and on the video where I actually implement the midpoint circle algorithm, I start with one of the versions of the algorithm that appears on the web, and I make some changes to it, and in the end we finally end up with this version here again. But I thought it would be good in this video just to derive this directly from first principles so we can see where it comes from and that it's actually correct.